Yeah, great. Yeah, you can introduce.
Okay, so welcome everyone to the Math Club talk. Today, the talk is about polygonal number triples, and it will be presented by Rahil Miraj, who is currently in second year of B.Math. He is primarily interested in number theory, and he also has published papers in resonance. Okay, so over to Rahil. You can start the talk.
Am I audible?
Yes.
Okay. Good afternoon. So our today's topic is polygonal number triples, and let's begin. So it is actually one of my research works where I have proposed that the equation PSX plus PSY is equal to PSZ has an infinitely many positive integer solutions in x, y, z for some given integer s which is greater than or equal to 3, and where the PRK is the kth r-gonal number. And I'll also describe a method to generate the solutions of the equation, and I'll show a Python code which is written on the basis of that method to compute the solution. And an interesting thing I'll do is that I'll show the Ramanujan's door number problem, a well-known problem in number theory, is actually a special case of our theorem under the triangular number case. That is when s is equal to 3, and we will solve it by our method. So what is the polygonal numbers? So the polygonal numbers are the count of total number of dots which can be equally spaced to form a regular polygon in the plane. Like the triangular numbers are 1, then 3, 6, 10, 15, and so on. Similarly, the square numbers are 1, 4, 9, 16, 25, so on. Similarly, pentagonal numbers 1, 5, 12, 22, 35, hexagonal numbers 1, 6, 15, 28, 45, and we can see that these things are following some common pattern, and the patterns are like for the triangular numbers we have 1, then the next term is 1 plus 2, 3, and the next term is 1 plus 2 plus 3, this is 6, and so on. The nth term will be 1 plus 2 plus so on till n. And the square numbers are 1, then 1 plus 3, then 1 plus 3 plus 5, and so on. So the nth term will be 1 plus 3 plus so on till 2n minus 1. And pentagonal numbers are 1, 1 plus 4, 1 plus 4 plus 7, and so on till 1 plus 4 plus 4 on till this is 3n minus 2, right? Yeah. So we can see that the nth term is actually a sum of some arithmetic progression whose first term is 1 and which have some common difference. For the triangular number case, we have the common difference is 1, that is for r is equal to 3. We have the common difference is 1 for r is equal to 4. The common difference is 2, and r is equal to 5. The common difference is 3. So basically the common difference are r minus 2. So we have to find the sum of some arithmetic progression with initial value 1 and common difference r minus 2. So so the PRN will be 1, then 1 plus r minus 2, then 1 plus 2 times r minus 2, and so on till 1 plus n minus 1 times r minus 2. So this add up to n plus n times n minus 1 by 2 times r minus 2. So which is actually equal to r minus 2 times n square minus r minus 4 times n and divided by 2. So this is the general value of nth term of the subpolygonal number. So for n is equal to 3, we get the triangular numbers are like that, then square numbers are like that, and pentagonal numbers are k times 3k plus 1 by 2, and so on. So this way we can find any polygonal numbers. So now let's see some history. Famous mathematicians like Pythagoras, Diophantus, Fermat, Lagrange, Gauss, Cauchy, many of their works have somehow related to these polygonal numbers. And also some of the interesting topics in number theory that are perfect numbers, Fermat numbers, Fibonacci numbers, Lucas numbers, Pascal's triangle, binomial theorem, Pell's equations, they are also somehow related to these polygonal numbers. As for example, the binomial theorem, for the binomial theorem, we can see the n plus 1th binomial coefficient is actually n times n plus 1 by 2, and this is nothing but the n plus 1th triangular number. Also, the Pell's equations are some equations over the square numbers. So these are also polygonal numbers. And I have an interesting thing to show. Then I was in class 12th, I did a paper that is a relation between the solutions of Pell's equation and triangular numbers. There I have proposed two theorems that are Pell's equation for any Pell's equation, x square minus dy square is equal to 1. There exists an infinite sequence of triangular numbers Tm such that y can be written as y is equal to 2 times 2 Tm divided by d. So the polygon Pell's equations also related to the polygonal numbers in some different way. And another thing is that I'll show a relation with perfect numbers. So what are perfect numbers? Perfect numbers are the numbers n which is equal to the sum of its positive divisors excluding itself. So actually the sum of the positive divisors excluding itself is equal to itself, is equal to n. So those n's are the perfect numbers. And we have a theorem that is if 2 to the power k minus 1 is a prime, then n is equal to 2 to the power k minus 1 times 2 to the power k minus 1. This is actually a perfect number, and all the even perfect numbers are of that form. And we can see that actually this can be written as 2 to the power k times 2 to the power k minus 1 and divided by 2. And this is nothing but the 2 to the power k minus 1th triangular number. So perfect numbers are also related. Anyway, we have another interesting chronology towards the development of polygonal numbers. It is that Pythagoras was the one who have initiated the concept of polygonal numbers. Later, Diophantus derived that general formula. And in the year 1636, Fermat conjectured his famous polygonal number theorem, but without any proof. He had proposed that every positive integer can be expressed as a sum of at most r-gonal numbers for some given integer r which is greater than or equal to 3. In the year 1770, Lagrange proved this theorem for r is equal to 4, that is for every positive integer can be written as a sum of at most 4 square numbers. In the year 1796, Gauss proved his famous Ifka theorem in his book Disquisitiones Arithmetica, and this is nothing but the triangular number case of that polygonal number theorem. And finally, in the year 1813, Cauchy proved the theorem, the polygonal number theorem. Okay, so our today's topic is polygonal number triples. So what are polygonal number triples? I have defined a triple x, y, z of positive integers to be polygonal number triple if it satisfies the equation PSX plus PSY is equal to PSZ, where S is a given and strictly greater than or equal to 3, a positive integer. And we can see that when S is equal to 4, this will become Pythagorean triples, and which is actually square number triples according to our definition. And in one of my earlier works, I have shown that there are infinitely many triangular number triples, and there are also infinitely many Pythagorean triples. So our today's work will generalize this theorem. So our problem, according to the definition of polygonal numbers, will become like that, and this is actually s minus 2 times x square minus s minus 4 times x plus s minus 2 times y square minus s minus 4 times y, and this is equal to s minus 2 times z square minus s minus 4 times z. So our method is just to multiply s minus 2 to both the sides, then multiply by 4, and then add s minus 4 squared. And an extra one. So actually this will, then it will become 2 times s minus 2 x minus s minus 4 whole squared plus 2 times s minus 2 times y minus s minus 4 the whole squared, and this is equal to 2 times s minus 2 z minus s minus 4 whole squared and plus 1 extra s minus 4 squared. So this is actually of the form a square plus b square is equal to c square plus d square, and we have a general solution for this a square plus b square is equal to c square plus d square is that pq plus mn squared plus pm minus qn squared, which is equal to pq minus mn squared times plus em plus qn squared. So we will just compare these 4 things with these four things, and we can get these 4 equations, and the last one can be written as this, and we can see that pq and mn are symmetric. So we will just choose some values of p and q, then using this equation we can find the value of mn, then and we have taken without loss of generality, we have taken p and pq, m and n are positive integers, and by this equation we get the value of mn, and it's, let us say, its prime factorization will be like that: p1 to the power alpha 1, p2 to the power alpha 2, so on. So there are total alpha 1 plus 1 times alpha 2 plus 1 and so on till alpha r plus 1, number of ordered pairs of Mn can be found. So then by solving these three equations, we get the value of x, y, and z are like pq plus mn plus s minus 4 divided by 2 s minus 2, and similarly y and z. But now we have claimed that there are infinitely many positive integer solutions. But what is the guarantee that we can get some positive integers by picking some pqmn? That is, what is the guarantee that 2 times s minus 2 should divide the numerator? So we will show this in the next lemmas. So the lemma 1 says that let pq, m, and n be the solutions of the equation pq minus mn is equal to plus minus s minus. Then for any given s which is greater than or equal to 3, p is equal to s minus 1, q is equal to s minus 2, m is equal to s minus s square minus 4s plus 6, n is equal to 1, or p is equal to s minus 2, q is equal to s minus 1, m is equal to 1, and n is equal to s square minus 4s plus 6 will give the integer values of x, for x is equal to that, y is equal to that, and z is equal to that. So we will just plug these values and show that this will give us some integer. Okay, so pq minus, at first we will check our fundamental equation. So the pq minus mn will be s minus 4, and then x will be s minus 1. This is an integer. Then y will be s square minus 3s plus 4 by 2. This is also an integer. Actually, s square minus 3s can be written as s times s minus 3. So this is even number, so divided by 2 will give integer. And similarly, z will become s square minus 3s plus 6. This is also an integer. Similarly, if we plug the next 4 values of pqmn, we can get the same, only we will get pq minus mn is equal to minus of s minus 4, and rest are same. Therefore, we have get there should exist a solution to our equation. But how many solutions are there? Our claim was that there are infinitely many solutions. So now we will show it. So the lemma 2 says that if pm is greater than or equal to qn, then for every solution x, y, z corresponding to the tuple p, q, m, and n, there is a higher solution x dash, y dash, z dash, which can be attained with p dash is equal to p plus 2n times s minus 2, q dash is equal to q, m dash is equal to m plus 2q times s minus 2, and n dash is equal to n. And here, if we plug the values of p dash, q dash, m dash, and n dash, we get this, and this will be pq minus mn, and which is equal to plus minus s minus 4. So x dash will be, by plugging the values, we get x dash will be x plus 2 times qn, and which is strictly greater than x. Similarly, we can get y dash is equal to y plus pq plus mn plus 2qn times s minus 2. Here actually this mod opens with a positive sign as for the choice of pqmn, and this is also greater than y, and we get the z dash will become this, and this is also greater than z. So x dash, y dash, and z dash is a higher solution. Similarly, if pm is less than or equal to qn, then for every solution x, y, z corresponding to the tuple pqmn, there is a higher solution x dash, y dash, and z dash, which can be attained with p dash is equal to p, q dash is equal to q plus 2m times s minus 2, m dash is equal to m, and n dash is equal to n plus 2p times s minus 2. And the method is just the same as previous lemma 2, and we will get this x dash is equal to x plus 2pm, then y dash is equal to that, and z dash is equal to that. So we have found some higher solutions, x dash, y dash, z dash, and so our plan was that to show that there exists at least one solution. Then we have shown that from one solution we can generate some higher solution. So proceeding this way, we can generate an infinitely many positive integer solution. So that was our our problem, and let us see some examples. So the example 1, we have taken that s is equal to 5. That is a pentagonal number. These are some pentagonal number triples, 35, 35, 70. Actually, the triples are that, and similarly, there are some other triples, and corresponding and the polygonal number, pentagonal numbers corresponding to that triples. And here is s is equal to 19. So the 19 gonal number triples are, some of them are that, and those are the corresponding 19 gonal numbers. There should be a comma. Yeah. And this is 100 gonal numbers. These are getting big, and the corresponding triples. And this is 199 gonal numbers. So now I will show the Python code. Actually, the code is written on the basis of our method, and here the user have to input. So I'm showing the code. So the user have to input the value of s, and then here I have generated some infinite loops so that it will try to find the values up to we terminate the program. So I'm running the program. So can you suggest some value of s from the audience?
S equal to 10.
Okay, so let's try with 10. See, the program is giving solutions. These are some solutions, and something in the chat. 1000. So 1000 is a bit big, so I think it will take time. And okay, so please give some smaller values. 31. Okay. Great. So it is working and giving solution. Let's terminate it and go back to our presentation. And I did an interesting thing. That is, I have run the code with Ramanujan's number. That is, so I had run the program with the Ramanujan number, and I showed it run with around 10 days, and it have given 5 to 6 solutions, and then I have terminated the program. And the solutions are really huge numbers. Like about 10 to the power 9, on the order of 10 to the power 9 or something else. Anyway, so now the door number problems. So what is door number problem? It is in the year 1914, then Ramanujan and his friend P.C. Mohalnobis were in Cambridge, and one day Mohalnobis asked Ramanujan to find the solution to a problem that he have read in the English magazine Strand. And the problem was to find the number x on a particular house of a street where the houses were numbered 1, 2, 3, and so on till k. And the sum of the house numbers to the left of x is same as the sum of the house numbers to the right of it. So, and the total number of houses are in that range. So there are some houses were numbered 1, 2, and so on. There is some house x, and there are total k houses. And it is saying that the sum of the house numbers to the left of x is equal to the sum of the house numbers to the right of it. So we will just add 1 plus 2 plus so on till x to both the sides. So it will become 1 plus 2 plus so on till x minus 1, and sum plus 1 plus 2 plus so on till x, and this is equal to 1 plus 2 plus so on till k, and this is actually x times x minus 1 by 2 plus x times s plus 1 by 2, and this is equal to 1 k times k plus 1 divided by 2. So this is actually a triangular number triple. And that is s is equal to 3, and the special case was y is equal to x minus 1. Actually, we should have write this here. Anyway, so I will solve it by our method. It is saying that if we choose PQMN as 12, 17, 41, and 5, we will get the desired solution. So let us compute the solution. Here, the solution. Okay, so if we take x is equal to 12 times 17 plus 41 times 5, and s minus 4 is just minus 1. And this is, and this divided by 2 times s minus 2 is just 2. So this will be 204 plus 205 minus 1 by 2. So which is equal to 204. And for the z, we will, z is equal to 12 times 41 plus 17 times 5 minus 1 and divided by 2. So this is 492 plus 85 minus 1 by 2. So which is equal to 288. So that we have a street with the door numbers are 1, 2, so on till 288, and where we have the door number, the solutions of our door number problem is 204, so that the house numbers to the left of it is equal to the sum of the house numbers to the right of it. So that's it. So in the polygonal numbers are some interesting topics in number theory, and many of its properties have been found before. And in this work, we have defined a new triple of polygonal numbers, which is a generalization of polygonal Pythagorean triples. And we have shown that there exist an infinitely many such triples, and we have developed a method to find these triples. And we have shown a Python code which is written on the basis of that method. And this code will give us the solution. So this is, I think this is an interesting topic, and in future one can try to find some other properties of this polygonal number triples and its application. So I would like to thank the referee and the editor for their fruitful suggestions, and I'm also grateful to the professors of our institute and my fellow friends for their hearty support. And these are the references. This paper has been accepted in Resonance and maybe published in next year or in this year. So thank you.
Hello, everyone. If you have any questions, feel free to ask. Rahil is here to answer.
Hello.
Yes, Prognath.
Yes, one of my questions is how did you arrive at this? What was the inspiration of arriving at these numbers actually? Finding the solutions. Was it just hard work? Or is there a trick behind how to get the inspiration of how to take the triples like that?
Actually, now this is a time when we don't do anything by our hands. So computer will find then.
So the choices of P, Q, M, and X, Y, Z. How to frame the numbers like that?
I didn't understand your question. Please repeat your question.
While you were solving the problem, how did you get at these numbers? The triples like that. What should I take the values of P, Q, M, N?
We have to choose some arbitrary value of PQ, and using this equation, we can find the values of Mn as I have mentioned, and then we will try to check that whether this PQ and Mn will give the integer values of X, Y, Z or not.
Okay.
And actually, in the code, I have did something like we have taken for P is equal to 1, then Q is equal to 1, and there is an infinite loop, and it will check for all values of P and Q, then find the values of Mn and check whether the X, Y, Z are integer or not by just plugging the values of into our equation.
All right. So,
I have a question. Is this the only infinite set of solutions that you can find, or has that not been?
No, actually, there are some other solutions. Okay, I'm showing the part. Okay, so here is that we have chosen some 4 values of P, Q, M, and N, and then another 4 values of P, Q, M, N, and but I have seen that some other set of values can also give the integer value. So I didn't mention that, but I should have mentioned it. Yeah. So
there are infinite sets of infinite solutions.
Yeah, actually this is it. Infinite set of infinite solutions. And
okay.
it may be one of its extension work. We can say something about this infinite set of infinite solutions
by varying the coefficients of the quadratic equation.
Exactly.
If there are no more questions, I guess we'll call it a day. And Rahil, if you could just stop the recording.
Yeah, sure.